In the last class we saw an important aspect or an important concept that we will use repeatedly in classical thermodynamics, that is the concept of state variable values not depending on the path taken between the two states. To understand that a little better, the example that we had considered was taking multiple routes between two destinations 1 and 2 in a mountainous region, and if we are interested in the difference in heights between 1 and 2, let us say, then the height being a state variable which depends only on the state of the system or the state 1 or the state 2 and not on the path in between them, irrespective of the path that we take, the value of the difference in the state variable or the difference in heights in this case will always be the same. This is a very powerful concept or an idea that we will repeatedly use. This route where the altimeter was available gave us a means of measuring. Similarly, we would have routes in thermodynamics between two states, various paths, and one of those paths would have some easy way of measuring the state variable between the state variable values at these 2 points. This was one important aspect. Then we started looking at equations for a closed system, useful thermodynamic equations for a closed system. Let us start with that again for this particular class. We had just done one last time. For a closed system, we have already seen from the definition of enthalpy H from equation 2.1, enthalpy, it is defined as U plus PV. Therefore, the total differential of enthalpy dH is d of U plus PV, and if we use the rules of differentials, it will be du plus, using chain rule here, it will be first function into derivative of the second function plus the derivative plus the second function into derivative of the first function, that is PdV plus VdP, and we already know du is TdS minus PdV, that was our equation 2.5 earlier, and if we substitute this here, we have TdS minus PdV plus PdV, so these two will cancel out and we have dH equals TdS plus VdP. This is equation 2.6 that we ended up with the last class. There are other useful equations or relationships that we can derive for the other thermodynamic variables, and let us see some of them here. If you recall the definition of the Helmholtz free energy A, we had defined it as U minus Ts. If you want, you can go back and check equation 2.2 in your notes or in the video lectures. A equals U minus Ts. Therefore, the total differential of A, following the same scheme earlier, is nothing but du minus, by chain rule, TdS minus SdT, and we already know that du equals TdS minus PdV from equation 2.5, and therefore if you substitute TdS minus PdV here, TdS minus PdV minus TdS minus SdT, TdS minus TdS will get cancelled out, and therefore we are left with dA equals minus SdT minus PdV, and we will call this equation 2.7. So we have looked at internal energy U, enthalpy H, Helmholtz free energy A, and the only other thermodynamic variable that we have defined so far is the Gibbs free energy G. According to our definition of Gibbs free energy, G equals H minus Ts, enthalpy minus the product of temperature and entropy. Same scheme as earlier, dG equals dH minus TdS minus SdT. We know that dH is TdS plus VdP, this we have already seen when we derived equation 2.6. Now if we substitute TdS plus VdP for dH, you can see that this TdS and this minus TdS will get cancelled out, and what we are left with is dG equals minus SdT plus VdP. Let us call this equation 2.8. Remember, we have derived these equations for a closed system. It is useful to see all these equations together, so let us see that, and it is nice to have it in one place for reference later, therefore let us do that now. So for a single component, single phase closed system, the following equations are valid, which we just derived. Du equals TdS minus PdV, this was our equation 2.5. dH equals TdS plus VdP, equation 2.6. dA equals minus SdT minus PdV, equation 2.7. dG equals minus SdT plus VdP, equation 2.8. Usually these useful relationships become a part of us because of repeated use, but for examination purposes, for your university examination purposes, you might want to remember these equations. You can always derive them quite simply from first principles, as we have shown. So far we had looked at a single component system, 1 mole of that system, and that being a closed system. Now let us slightly complicate the system. Let us increase the number of moles of the pure component. Okay. Earlier it was 1, let it now be more than 1. It is still a closed system, it is still a pure component, and only the number of moles are more than 1. If that is the case, remember we had used U, S, H, A, G for 1 mole of the substance, the thermodynamic quantities for 1 mole of the substance. Now since the number of moles are greater than 1, let us use a slightly different terminology so that there is no confusion later. So the terminology for the thermodynamic variables of a system consisting of, let us say, n moles of a pure component is U total, represented as UT, S total ST, H total HT, A total AT, G total GT, and V total VT. The 4 equations that we derived for a closed system earlier, for 1 mole of a closed system, a closed system consisting of 1 mole of a pure component earlier, are valid even in this case. I am not going to prove that in this particular lecture. If you need proof, you can see one of your reference books, which is by Kenneth Denby. Let me just state the equations here. DUT equals TDST. Remember that T is an intensive variable, its value will not depend on the amount of substance present, so it is going to be T DST minus P dVT. P is also an intensive variable. Let us call this equation 2.5a. DHT is TDST plus VT dP, equation 2.6a. You can compare these equations with the equations for 1 mole of a pure substance. DAT equals minus ST dt minus P dVT, equation 2.7a, and DGT equals minus ST dt plus VT dP, which is equation 2.8a. To re-emphasize, these are the equations for a system that consists of n moles of a pure substance and the system is a closed system. Now let us look at a slightly higher level of complication. Let us stick ourselves to one phase, let us say a gas phase or a liquid phase, just one phase there, but now let us increase the number of components from one earlier. If you had only one component, it was a pure substance. Let us increase the number of components from one to many. Now we have a multi component system, but still let us work in single phase. Therefore, we are looking at a multi component system, but a homogeneous system. For example, it could be a mixture of gases of different species. It is all going to be in the gas phase, but it is going to consist of many different species. The air is a very good example of a multi component homogeneous gas phase system. Air has predominantly nitrogen, oxygen, but you also have carbon dioxide, you also have water vapor, and so on and so forth. So this is an example of a multi component homogeneous system. Let us look at some of the relationships that will be useful for a multi component single phase system. Before we do that, we need to know some terminology that we will use here. Let N1 be the number of moles of component 1, N2 be the number of moles of component 2, and so on. If you recall our equation 2.5, du equals TdS minus PdV, you can recall that we took the internal energy U as a function of S and V. It will become clearer when I say the next thing, and for saying the next thing, let me extend this to a k component case. This U as a function of S and V that we took to write for equation 2.5 was limited for a single component system or a pure substance. Now we are extending this to a k component case. Since it has k components, it has to be indicated by the total internal energy, and let us say that this is a function of entropy, total volume, and since it is a multi component system, it will definitely depend on the number of moles of each component present, and we are taking k components to be present. So N1 number of moles of the first component, N2 number of moles of the second component, and so on till Nk number of moles of the kth component. We will call this equation 2.9. Therefore, the total differential of Ut, if you recall the way the total differentials are written, is the partial differential of Ut with respect to St at constant other variables, or at the conditions where the other variables are held constant, which is Vt, N1, N2, N3 are all held constant, which is indicated by Ni being constant. So dou Ut by dou St times dSt plus dou Ut by dou Vt, the second variable, at constant St and all Ni times dVt plus dou Ut by dou N1 dN1 plus dou Ut by dou N2 dN2, and so on and so forth, and which can be indicated in short form as sum of I equals 1 to I equals k, because there are k components, dou Ut by dou Ni at constant Vt, St and Nj dNi. Note that the subscripts I and the subscripts j do not correspond to the same species. We are taking the partial differential with respect to one of the species when all the other species are held constant. This is a notation to indicate that, and this will be consistent. This will help us in developing a consistent notation for representing this kind of a situation throughout the course. So summation of I equals 1 to k dou ut by dou ni Vt at constant Vt, St and Nj times dni. This is the total differential. This comes from the theorem in mathematics where you can represent the total differential by this particular thing if it is an exact differential. We will call this equation 210. If we compare the first two terms of equation 210 that we just wrote down with equation 2.5a, I am going to give you both these equations now. This is 210 that we derived just now and this is 2.5a. Here going by the same scheme, dut is dou ut by dou st at constant v dst minus dou ut by dou Vt at constant St dVt. Okay. It is quite easy to see the correspondence between the two, and therefore it is quite straightforward to write dou ut by dou St at constant Vt Ni equals the temperature, and dou ut by dou Vt at constant St and all other components, the number of components being held constant, as minus P. Note that this is for a multi-component system and we have compared it with a single component system and we are drawing useful relationships. Now let us define, let me go back a little bit, let us look at this quantity a little more closely, dou ut by dou ni at constant Vt, St and J. Let us define that quantity dou ut by dou ni at constant Vt, St and J as something called mu I, where mu I is actually called the chemical potential of species I. Note this term chemical potential, this is going to be a very important intrinsic variable in this entire course, so please take a note of this. I will call this equation 2.11. Therefore, in terms of whatever we have defined just now, the chemical potential, we can write our equation 210 that we saw earlier as dut equals T dst minus P dVt plus summation of summation over I mu I dni. We will call this equation 212, excuse me. So that was for internal energy. Let us follow a similar argument for the total Gibbs free energy G. Gt we know, rather let us take Gt as a function of temperature, pressure and all the number of moles of the components. So N1, N2 till Nk, equation 213. Therefore, the total differential Gt dGt can be written as dou Gt by dou T at constant P all other Ni or all Ni dt plus dou Gt by dou P at constant T Ni dP plus, as we have seen, dou Gt by dou N1 at constant T Np and all other Nj's dN1 dou Gt plus dou Gt by dou N2 at constant T Np all other Ni's dN2 and so on, which can be represented in short form as summation of I over 1 to k, summation over I from 1 to k dou Gt by dou Ni at constant Tp Nj, where we already saw that I and J will not be the same, times dNi. I will call this equation 214. If we compare this 214 with 2.8a, which is for a pure component system or a single component system, dGt equals minus SdT plus Vt dP, we can write dGt equals minus St dt plus Vt dP plus the remaining term which comes in for the multi component case, since we have for a multi component case Gt to be a function of all other components also, the amounts of components also. So we have this extra term here, summation of mu I dni. We will call this equation 215. Let us define dou Gt by dou Ni at constant temperature, pressure and Nj, which is this quantity, as mu I itself. That is what I have done here when I wrote this equation. Somebody can ask me this question now. You had earlier said that dou Ut by dou Ni at certain variables being constant, St, Vt and Ni is being constant, Nj is being constant, you had defined as mu I, whereas now you are defining dou Gt by dou Ni at constant Tp and Nj as mu I. How can you do that? Let us now go ahead and show that these two quantities are actually the same. To justify, let us begin with equation 212, where we first defined our mu I. We started with dut equals Tdst minus P dVt plus summation of mu I dni. Let us add d of the total the differential of this particular quantity Pvt minus T St to both sides of equation 212. If we do that, dut plus d of Pvt minus T St equals Tdst minus P dVt plus the same quantity on the right hand side plus summation of mu I dni. Note that we can combine these together, they are additive, the differentials are additive. You can visualize the differential in a graph or in a 2-dimensional graph or a 3-dimensional graph, then you can understand why this is additive. So if we recognize that this is additive and you can expand the term on this side using chain rule, let us do that. Therefore d of ut plus P Vt minus Tst equals Tdst minus Pdv we already had. Now if we expand the term that we added by chain rule, we have P dVt plus Vt dP minus Tdst minus St dt plus whatever remained there, which is summation of mu I dni. We can cancel Tdst and minus Tdst. We can also cancel plus P dVt and minus P dVt, and therefore dGt equals minus St dt plus Vt dP plus summation of mu I dni. Note that this term automatically became dGt and whatever was left here was only minus St dt plus Vt dP plus summation of mu I dni, and this was the same mu I that we started with earlier, we did not do anything to it, and therefore the mu i's in equation 211, which was for the internal energy dut, and equation 216 for the Gibbs free energy dGt are the same. So although we had used different ways to define the chemical potential, they all turn out to be the same quantity. Let us look at this equation 216 a little closer. It is a very useful equation. Dou Gt divided by dou Gt by dou Ni at constant temperature, pressure and all other mole numbers remaining constant, we had defined as mu I. Note that we have defined mu I in the context of a multi component system, that is purely didactic, that is purely to facilitate a certain flow in the development of the subject. The chemical potential itself is an intrinsic quantity for a particular system, and therefore whether the system is multi component or whether it is a single component or whatever other combinations you may have, the concept of chemical potential is still valid for any system that you take. Okay. To put a little more formally, written here, although the chemical potential mu I was introduced in the context of a multi component system, it is an intrinsic thermodynamic property, thus it is an equally valid concept for a pure component also. Let us look at this a little closer now. Look at the quantities that are being held constant in this definition: dou Gt by dou Ni at constant temperature, pressure and all other Nj's different from Ni, which is taken for the differentiation. These are very easy to maintain constant in an experimental situation, and therefore this definition of chemical potential has significant experimental relevance, and because of that, although you could define chemical potential as dou Ut by dou Ni at certain variables constant, dou At by dou Ni at certain other variable constant and so on and so forth, this definition is most commonly used. I have already mentioned this, but let me complete the definitions here. So by extension, as mentioned earlier, we can define chemical potential in terms of enthalpy H or the Helmholtz free energy A. Therefore, for a multi component single phase system, dUt equals Tdst minus P dVt plus summation of mu I dNi, equation 212. We are just compiling all the equations together, we will have it at one place for easy reference later. dGt equals minus St dt plus Vt dP plus summation of mu I dNi or all I, equation 215. dHt equals Tdst plus Vt dP plus summation of mu I dNi, equation 217, and dAt equals minus St dt minus P dVt plus summation of mu I dNi, we will call this equation 218. What I would like you to do is to actually sit down and verify the same way that we did that these two mu i's were the same. It will be good if you verify and convince yourself that these two mu i's are also the same and they are the same as the other mu i's that are here. That way there will be no doubts in your mind. These are the four equations that we have just derived. I would like to point out some interesting features here. These four equations: dUt equals Tdst minus P dVt plus mu I dNi, dHt equals Tdst plus Vt dP plus mu I dNi, dAt equals minus St dt minus P dVt plus mu I dNi, and dGt equals minus St dt plus Vt dP plus mu I dNi. Summation. Let us look at it in terms of writing a total differential in terms of its partial differentials. This term, as you can recall, can be written as dou Ut by dou St at constant Vt Ni, and both these held constant, and this term can be written as dou HT by dou ST at constant P and Ni. Similarly, this term P can be written as dou UT by dou Vt at constant St and Ni. The same P here which appears in this other equation can be represented in terms of the Helmholtz free energy as dou At by dou Vt at constant T and Ni. Now you get the scheme with which we are going to do things. Minus St is dou At by dou T at constant Vt and Ni. Let us look for another St. It is here. St minus St equals dou Gt by dou T at constant P and Ni. Similarly, this Vt can be written as dou Ht by dou P at constant St and Ni, and Vt which appears here can be written as dou Gt by dou P at constant T and Ni. And as we have already seen, the chemical potentials can be written in terms of either the partials of Ut with Ni at constant St, Vt and all other Nj's. Here in terms of enthalpy you could write mu I as dou Ht by dou Ni at constant S, T, Vt and all other Nj's, dou At by dou Ni at constant T, V and all other Nj's, and dGt at constant dou Gt by dou Ni at constant Tp and all other Nj's. If we put this all together in one place, we can say our temperature can be represented as the partial of Ut with respect to St at constant Vt Ni, or partial of Ht with St at constant P Ni. Okay, we had seen T appearing in two different equations there, and which represented which we represented as partial derivatives. I am just compiling those here as equation 219, P as minus of dou Ut by dou Vt at constant St Ni, or minus dou At by dou Vt at constant T Ni, equation 220, St as minus of dou Gt by dou T constant P Ni, or minus of dou At by dou T at constant Vt Ni, equation 221, and Vt as dou Gt by dou P constant T Ni, or dou Ht by dou P at constant St Ni, equation 222, and all the four ways of representing the chemical potential as either dou Ut by dou Ni at constant V, Vt, St, Nj, dou Gt by dou Ni at constant Tp, Nj, dou Ht by dou Ni at constant St, P, Nj, or dou At by dou Ni at constant T, Vt, Nj. Let me call this equation 223. These are very useful equations, as we will see in a little while. I will give you an example and we will use this again and again in this course. Let us now look at something called a Gibbs-Duhem equation. This is a fundamental equation in classical thermodynamics, and as we go along let us see the features of that, but now let us derive the Gibbs-Duhem equation. Let us consider equation 215, which is dGt equals minus St dt plus Vt dP plus summation of mu I dni. Now this is a differential. Let us integrate this equation at constant T and constant P. If it is constant t, this term will completely vanish, and if it is constant p, this term will completely vanish. And also let us retain the relative proportions of the components in the system while we are integrating the equation, which means the mu i's are also being held constant. Integration can be viewed as increasing the size at this under the same conditions as the small aspect that we initially looked at. Therefore, if the initial values were Ni, Gt, St and Vt of the system, the final values when it has been integrated or it has been made big could be Kni, Kgt, Kst and Kvt. The values have increased k-fold. It is quite easy to see, these are all extensive quantities. If you have k number of moles, the other variables are going to increase k times, and therefore it is quite valid to write this, and we are viewing the integration as increasing the size of the system. Okay, now we are integrating this equation dgt minus st dt equals minus st dt plus vt dp plus summation of mu I dni, and we are looking at this integration as increasing the size of the system. Initially it had let us say 1 mole, and it is now going to k moles, and therefore the values of the extensive variables initially were, let us say, Ni number of moles, Gt the total Gibbs free energy, St the total entropy, and Vt the total volume, to the final values which is k times that of the initial values. Now if we do that, the delta Gt, which is the integrated value, the difference between the values of the two states, say 1 and 2, delta Gt equals, since we had taken it at constant temperature, the first term turns to 0, at constant pressure the second term goes to 0, and the third term summation of mu I delta Ni, where delta Gt equals Kgt minus Gt. Remember I mentioned about the difference between the final value and the initial value, and therefore which can be it can be written as k minus 1 times Gt, and our delta Ni is nothing but k times Ni minus Ni, which can be written as k minus 1 times Ni. Substituting these values back into the integrated expression, k minus 1 times Gt equals summation of mu I into k minus 1 times Ni, or this k minus 1 is a constant, it can be taken out and cancelled. Gt equals summation of mu I Ni. Let us call this equation 223a. From that equation, delta G equals summation of mu I Ni. If we take the total differential of that expression, we get dgt equals mu I dni, the first term, the first function into the derivative of the second function, but it is summed over all terms, therefore this will just be a sum plus the other part of the differential in the chain rule, Ni times d mu I. Let us call that equation 2.23b. If we compare 2.23b with 2.15, I would like you to compare yourself, we can write minus st dt plus vt dp minus summation of ni d mu I. If you substitute the expression for dgt and cancel the common terms here, we get minus st dt plus vt dp minus summation of ni d mu I. This mu I dni will get cancelled with plus of mu I dni, which appears in dgt, and that equals 0. let us call that equation 223C. This equation minus ST dt plus Vt dP minus summation of Ni d mu I equals 0 is called the Gibbs-Duhem equation. Note, although we, while deriving this equation, we had made assumption about constancy of temperature and constancy of pressure, the final equation that we have is in terms of state variables. What does a state variable mean? Its value depends only on the state of the system and not on the path taken to reach the two states. A constant temperature process or a constant pressure process are all paths between the same two states, and therefore whatever had been the path, say a constant temperature and a constant pressure and so on and so forth, this final equation here is valid for all conditions because they are in terms of the state variables. Note the variables that are here: St, the total entropy, which is a state function; temperature, state function; Vt, it's a state function; P, pressure, state function; Ni, the number of moles, depends on the state; mu I definitely depends on the state. Therefore this is a variable of this is an equation of all state variables, and therefore this is valid in general. Also note that this equation is the relationship between simultaneous variations in the intrinsic parameters. That is what makes this equation special. This is temperature, this is pressure, this is chemical potential, dt the variation in temperature, dp the variation in pressure, and d mu I the variation in chemical potential, and this equation gives us a nice relationship when all three are varied simultaneously. That is the another special thing about the Gibbs-Duhem equation. When we begin the next class, let us look at Maxwell's relations, which are very useful relations that we can derive from whatever we have learnt so far, and by applying a basic theorem in calculus to the equations that we have derived so far. That we will start doing in the next class.